voices to allow you to drift off. Whatever you do, I hope you get the desired result. Here we go. 4.1 Introduction. Before writing a program to solve a program, you should have a thorough understanding of the problem and a careful, planned approach of solving it. When writing a program, you also should understand the available building blocks and employ proven program construction techniques. In this chapter and the next, we discuss these issues in presenting the theory and principles of structured programming. The concepts presented here are crucial in building classes and manipulating objects. We discuss Java's if statement in addition detail and introduce the if-else and while statements. All of these building blocks allow you to specify the logic required for methods to perform their tasks. We also introduce the compound assignment operator and the increment and decrement operators. Finally, we consider the portability of Java's primitive types. 4.2 Algorithms. Any computing problem can be solved by executing a series of actions in a specific order. A procedure for solving a problem in terms of 1. The actions to execute, and 2. The order in which these actions execute is called an algorithm. The following example demonstrates that correctly specifying the order in which the actions execute is important. Consider the rise and shine algorithm, followed by one executive for getting out of bed and going to work. 1. Get out of bed. 2. Take off pajamas. 3. Take a shower. 4. Get dressed. 5. Eat breakfast. 6. Carpool to work. This routine gets the executive to work well, prepared to make critical decisions. Suppose that the same steps are performed in a slightly different order. 1. Get out of bed. 2. Take off pajamas. 3. Get dressed. 4. Take a shower. 5. Eat breakfast. 6. Carpool to work. In this case, our executive shows up for work soaking wet. Specifying the order in which statements, actions, execute in a program is called program control. This chapter investigates program control using Java's control statements. 4.3 Pseudocode. Pseudocode is an informal language that helps you develop algorithms without having to worry about the strict details of Java language syntax. The pseudocode we present is particularly useful for developing algorithms that will be converted to structured portions of Java programs. The pseudocode we use in this book is similar to everyday English. It's convenient and user-friendly, but it's not an actual computer programming language. You'll see an algorithm written in pseudocode. You may, of course, use your own native language to develop your own pseudocode. Pseudocode does not execute on computers. Rather, it helps you think out a program before attempting to write it in a programming language, such as Java. This computer provides several examples of using pseudocode to develop Java programs. The style of pseudocode we present consists purely of characters, so you can type pseudocode conveniently using any text editor program. A carefully prepared pseudocode program can easily be converted to a corresponding Java program. Pseudocode normally describes only statements representing the actions that occur after you convert a program from pseudocode to Java, and the program is run on a computer. Such actions might include input, output, or calculations. is reserved by Java and should not be used as an identifier in programs. The research of Poland and Jacopini demonstrated that programs could be written without any go-to statements. The challenge of the era for programmers was to shift their styles to go-to-less programming. The term structured programming became almost synonymous with go-to elimination. Not until the 1970s did most programmers start taking selection statement because it selects between two different actions or groups of actions. The switch statement is called a multiple selection statement because it selects among many different actions. 4.3 Iteration statements in Java. Java provides 4 iteration statements, also called repetition statements or looping statements, that enable programs to perform statements repeatedly as long as a condition, called the loop continuation condition, remains true. The iteration statements are while, do, while, for, and enhanced for. Just in case, do, while is one of the iteration statements. Chapter 5 presents the do, while, and for statements, and Chapter 7 presents the enhanced for statement. The while and for statements perform the action or group of actions in their bodies 0 or more times. If the loop continuation condition is initially false, the action or group of actions will not execute. The do while statement performs the action or group of actions while its body 1 or more times. Now let me repeat this. The do while statement performs the action or group of actions in its body 1 or more times. The words if, else, switch, while, do, and for are Java keywords. A complete list of Java keywords appears in Appendix C. 4.4.4 Summary of control statements in Java. Java has only 3 kinds of control state structures, which form this point forward. We refer to as control statements, the sequence statements, selection statements, 3 types, and iteration statements, 4 types. Every program is formed by combining as many of these statements as is appropriate for the algorithm the program implements. We can model each control statement as an activity diagram. Like figure 4.1, each diagram contains an initial state and a final state that represent a control statement's entry point and exit point, respectively. Single entry, single exit control statements make it easy to build programs. We simply connect the exit point of one of the entry point of the next. We call this control statement stacking. We'll learn that there's only one other way in which control statements may be connected. Control statement nesting, in which one control statement appears inside another. Thus, algorithms in Java programs are constructed from only 3 kinds of control statements, combined in only 2 ways. This is the essence of simplicity. 4.5 If single selection statement. Programs use selection statements to choose among alternative courses of action. For example, suppose that the passing grade on an exam is 60. The pseudocode statement, if student's grade is greater than or equal to 60, print passed, determines whether the condition student's grade is greater than or equal to 60 is true. If so, passed is printed, and the next pseudocode statement in order is performed. If the condition is false, the print statement is ignored, and the next pseudocode statement in order is performed. The indentation of the second line of the selection statement is optional but recommended because it emphasizes the inherent structure of structured programs. The preceding pseudocode if statement may be written in Java as if parentheses student grade is greater or equal to 60 close parentheses squiggly brackets system capital S dot out dot print line brackets double quotes passed semicolon close squiggly bracket. The Java code corresponds closely to the pseudocode. If this one of the properties of pseudocode that makes it such a useful program developing tool. UML activity diagram for an if statement. The figure contains decision symbol, which indicates that a decision is to be made. The workflow continues along a path determined by the symbol's associated card conditions, which can be true or false. Each transition energy emerging from a decision symbol has a card condition specified in square brackets next to the arrow. If a card condition is true, the workflow enters the action state to which the transition arrow points. In figure 4.2, if the grade is greater than or equal to 60, the program prints past the transitions of the activity's final grade. If the grade is less than 60, the program immediately transitions to the final state without displaying a message. The if statement is a single entry, single exit control statement. We'll see that the activity diagrams for the remaining control statements also contain initial states, transition arrows, action states that indicate actions to perform, decision symbols with associated card conditions that indicate decisions are to be made, and final states. 4.6 If-else double selection statement. The if selection statement performs an indicated action only when the condition is true, otherwise the action is skipped. The if-else double selection statement allows you to specify an action to perform when the condition is true and another action when the condition is false. For example, the pseudocode statement: if student's grade is greater than or equal to 60, print passed, else print failed. Prints passed if the student's grade is greater or equal to 60, but prints failed if it is less than 60. In either case, after printing occurs, the next pseudocode statement in sequence is performed. The preceding if-else pseudocode could be written in Java as if brackets grade is greater or equal to 60, close parentheses, squiggly brackets, system.out.println, parentheses, passed, double quotes, semicolon, close, squiggly brackets, else, and another squiggly bracket, system.out.println, parentheses, double quotes, failed, semicolon, close, squiggly bracket. The body of the else is also indented. Whatever indentation convention you choose should be applied consistently throughout your programs. 4.6.1 Nested if-else statements. A program can test multiple cases by placing if-else statements inside the other if-else statement to create a nested if-else statement. For example, the following pseudocode represents a nested if-else that prints A for exam grades greater than or equal to 90, B for grades 80 to 89, C to 70 to 79, D to 60 to 69, and F for all grades. The pseudocode may be written in Java as if student grade is greater or equal to 90, squiggly brackets, system.out.println, parentheses, double quotes, A, close squiggly brackets, else, squiggly bracket, if system grade is greater or equal to 80, squiggly brackets, system.out.println, parentheses, B, double quotes, semicolon, close semi brackets, and so on and so forth. Just in case, you would indent each if to else, and once you close that bracket and you need to nest more, you indent the next if and the next if. The if and the else stay on the same single statement can be placed. The following example includes a block of multiple statements. In the else part of an if-else statement, if parentheses grade is greater or equal to 60, close parentheses, squiggly brackets, system.out.println, parentheses, double quotes, past, close parentheses, semicolon, close, squiggly brackets, else, squiggly brackets, system.out.println, failed, semicolon, system.out.println, parentheses, you must take this course again, double quotes, close parentheses, semicolon. In this case, if grade is less than 60, the program executes both statements in the body of the else and prints failed. You must take this course again. Note the braces surrounding the two statements in the else clause. The braces are important. Without the braces, the statement system.out.println, you must take this course again, would be outside the body of the else part of the if-else statement and would execute regardless of whether this grade was less than 60. Syntax errors, such as a missing brace, are caught by the compiler. A logic error, e.g. when both braces in a block are left out of the program, has its effect at execution time. A fatal logic error causes a program to fail and terminate prematurely. A non-fatal logic error allows a program to continue executing but causes it to produce incorrect results. Just as a block can be placed anywhere a SQL statement can be placed, it's also possible to have an empty statement. Recall from section 2.8 that an empty statement is represented by placing a semicolon where a statement would normally be. 4.7 Student class listed if-else statements. Class student has features similar to those of class account discussed in chapter 3. Class student stores a student's name and average and provides methods for manipulating these values. Public class student, squiggly brackets, instance variables, private string name, private double average. Public student, parentheses, string name, double average, close parentheses, squiggly brackets. This dot name is equal to name, semicolon. That was the constructor that initializes the instance variables. The class student stored the student name and average. If parentheses average is greater than 0.0, close parentheses, squiggly brackets. If parentheses average is greater or equal to 100, close parentheses, squiggly brackets. This dot average is equal to average. That assigns to instance variable, and that validates that average is greater than 0.0 and is less than equal to 100.1. Otherwise, keep instance variable's average default value, which is 0, 0. Sets the student's name. How do we do this? Public void set name, parentheses string name, squiggly brackets. This dot name is equal to name. This retrieves the student's name. Public string get name, parentheses nothing within them, squiggly brackets, return name, semicolon, close squiggly brackets. This sets the student's average. Public void set average, parentheses, double student average, close parentheses, squiggly brackets. We're going to validate now if the average is less than 0.0 and less than or equal to 100.1. Otherwise, we keep the instance variable's average's current value. And I'm sorry, we validate the average is greater than 0.0. If the average, in parentheses, is greater than 0.0, close parentheses, squiggly brackets. If, in parentheses, average is less than or equal to 100.1, squiggly brackets again, this dot average is equal to average. parentheses, nothing within them, squiggly brackets, return average. And now we determine and return the student's letter grade. Public string get letter grade, parentheses, nothing within them, and then squiggly brackets. String letter grade is equal to quotes with nothing within them, and that is to initialize and to an empty string. If parentheses average is greater or equal to 90, close parentheses, squiggly brackets, letter grade is equal to A. Else if average is greater or less than 80, letter grade is equal to B. And we continue doing this with C and D. Else if letter grade is equal to F, close, return letter grade. The class contains an instance variable name of type string in line 4 to store a student's name. The instance variable average of type double, line 5 to store a student's average in a course. A constructor, lines 8 through 18, that initializes the name and average. In section 5.9, you'll learn how to express lines 13 through 14 and 40 or 34 through 35 more concisely with logical operators that can test multiple conditions. Methods set name and get name, lines 21 to 28, to set and get the student's name. Methods set average and get average, lines 31 through 44, to set and get the student's average. Method get letter grade, lines 47 through 67, which uses nested if-else statements to determine the student's letter grade based on the student's average. The constructor and method set average each use nested if statements, lines 13 through 17 and 34 through 38, to validate the value used to set the average. These statements ensure that the value is greater than 1 point and less than or equal to 100.0. Otherwise, average's value is left unchanged. Each if statement contains a simple condition. If the condition in line 13 is true, only then will the condition in line 14 be tested, and only if the conditions in both line 13 and line 14 are true will the statement in line 15 execute. 4.8 While iteration statement. An iteration statement allows you to specify that a program should repeat an action while some condition remains true. The pseudocode statement, while there are more items on my shopping list, purchase next item and cross it off my list, describes the iteration during a shopping trip. The condition, there are more items on my shopping list, may be true or false. If it's true, then the action, purchase next item and cross it off my list, is performed. This action will be performed repeatedly while the condition remains true. The statements contained in the while iteration statement constitute its body, which may be a single statement or a block. Eventually, the condition will become false when the shopping list's last item has been purchased or crossed off. At this point, the iteration terminates, and the first statement after the iteration statement executes. As an example of Java's while iteration statement, consider a program statement that finds the first power of 3 larger than 100. After the following while statement execute, products contain the result int product equals 3 semicolon, while parentheses product is less than or equal to 100. Close parentheses, squiggly brackets, product is equal to 3 times product, semicolon, close brackets. Each iteration of the while statement multiplies product by 3, so product takes on the values 9, 27, 81, and 234 successfully. The product becomes 230 or 43. Product less than or equal to 100 becomes false, state and a decision. The diagram introduces the UML's merge symbol. The UML represents both the merge symbol and the decision symbol as diamonds. The merge symbol joins two flows of activity into one. In this diagram, the merge symbol joins the transitions from the initial state and from the action state, so they both flow into the decision that determines whether the loop should begin executing. The decision and merge symbols can be distinguished by a number of incoming and outgoing transition arrows. A decision symbol has one transition arrow pointing to the diamond and two or more pointing out of it to indicate possible transitions from that point. In addition, each transition arrow pointing out of the decision symbol has a guard condition next to it. A merge symbol has two or more condition arrows pointing to the diamond and only one pointing from the diamond to indicate multiple activity flows merging to continue the activity. None of the transition arrows associated with the merge symbol has a guard condition. 4.9. Formulating algorithms. To illustrate how algorithms are developed, we solve two variations of a problem that averages student grades. Consider the following statement. A class of 10 students took a quiz. The grades, integers in the range 0 to 100, for this quiz are available to you. Determine the class average on the quiz. So here's what the pseudocode would look like. Set total to 0. Set grade counter to 1. While grade counter is less than or equal to 10, prompt the user to enter the next grade. Input the next grade. Add the grade into the total. Add 1 to the grade counter. Set the class average to the total divided by 10. Print the average. Now let's use this pseudocode and list the actions to execute and specify the order in which they should execute. We use counter control to the iteration to impute the grades one at a time. This technique uses a variable called a counter or control variable to control the number of times a set of statements will execute. Counter-controlled iteration is often called definite iteration because the number of iterations is known before the loop begins executing. In this example, iteration terminates when the counter exceeds 10. This section presents a fully developed pseudocode algorithm and a corresponding Java program that implements the algorithm. In section 4.10, we demonstrate how to use pseudocode to develop such an algorithm from scratch. Note the references in the algorithm of figure 4.7 to a total and a counter. A total is a variable used to accumulate the sum of several values. A counter is a variable used to count. In this case, the grade counter indicates which of the 10 grades is about to be entered by the user. Variables used to store totals are normally initialized to the 0 before being used in a program. In figure 4.8, class average's main method implements the class averaging algorithm described by the pseudocode. It allows the user to enter 10 grades and calculates and displays the message. Import java.util.scanner, public class average, squiggly brackets, public static main, or void main, string args, scanner input equals new scanner, system.in, int total equals 0, int grade counter equals 1, while, parentheses, grade counter is less than or equal to values entered by the user. Lines 11, 12, 17, and 24 declare local variables total, grade counter, grade, and average, respectively, to be of type int. Variable grade stores the user input. These declarations appear in the body of method main. Recall that variables declared in a method body are local variables and can be used only from the line of their declaration to the closing right brace of the method declaration. A local variable's declaration must appear before the variable is used in that method. A local variable cannot be accessed outside the method in which it's declared. Variable grade declared in the body of the while loop can be used only in that block. Initializing phase, initializing variables total and grade counter. The assignments in lines 11 through 12 initialize total to 0 and grade counter to 1. These initializations occur before the variables are used in the calculations. Processing phase, reading 10 grades from the user. Line 15 indicates that the while statement should continue looping, also called iterating, as long as grade counter's value is less than or equal to 10. While this condition remains true, the while statement repeatedly executes the statements while the braces that delimit the body. Line 16 appears the prompt enter grade. Line 17 enters the grade entered by the user and assigns it to variable grade. Then line 18 adds the new grade entered by the user to the total and assigns the result to total, which replaces its previous value. Line 19 adds 1 to grade counter to indicate that the program processed a grade and is ready to input the next grade from the user. Incrementing grade counter eventually causes it to exceed 10. Then the loop terminates because its conditions, line 15, become false. Termination phase, calculating and displaying the class average. When the loop terminates, line 23 performs the averaging calculation and assigns its result to the variable average. Line 26 uses system.out's printf method to display the text total of all 10 grades is, followed by variable total's value. Line 27 then uses printf to display the text class averages, followed by variable averages value. When execution reaches line 28, the program terminates. Notice that this example contains only one class, with method main performing all the work. In this chapter, and in chapter 3, you've seen examples consisting of 2 classes, one containing instance variables and methods that perform tasks using those variables, and one containing method main, which creates an object of the other class and calls its methods. Occasionally, when it does not make sense to try to create a reusable class to demonstrate a concept, we'll place the program statement entirely within the single class's main method. A note about arithmetic overflow. In figure 4.8, line 18 added each grade added by the user to the total. Even this simple statement has a potential problem. Adding the integers could result in a value that's too Receiving user input. Whenever a program receives input from a user, various problems might occur. For example, in line 17, we assume the user will add an integer grade in the range of 0 to 100. However, the person entering a grade could enter an integer less than 0, an integer greater than 100, an integer outside the range of values that can be stored in an int variable, a number containing a decimal point, or a value containing letters or special symbols that's not even an integer. To ensure that inputs are valued, industrial strength problems must test all possible erroneous cases. A program that inputs grades should validate the grades by using range checking to ensure that they are values from 0 to 100. You can then ask the user to re-enter any value that's out of range. If a program requires inputs from a specific set of values, you can ensure that each input matches the value in a set. 4.10 Formulating algorithms. Sentinel controlled iteration. Let's generalize section 4.9's class average problem. Consider the following problem. Develop a class averaging program that processes grades for an arbitrary number of students each time it's run. In the previous class averages example, the problem statement specified the number of students, so the number of grades 10 was known in advance. In this example, no indication is given of how many grades the user will enter during the program's execution. The program has processed an arbitrary number of grades. How can it determine when to stop the input of grades? How will it know when to calculate and print the class average? One way to solve this problem is to use a special value called a sentinel value, also called a signal value, a dummy value, or a flake value, to indicate end of data entry. The user enters grades until all legitimate grades have been refinement of the preceding pseudocode statement is then, and this is in pseudocode of course, prompt the user to enter the first grade, input the first grade, possibly the sentinel. While the user has not yet entered the sentinel, add this grade into the running total. Add 1 to the grade counter. Prompt the user to enter the next grade, input in the next grade, possibly the sentinel. In pseudocode, we do not use braces around the statements that form the body of the while structure. We simply indent the statements of the while to show that they belong to the while. Again, pseudocode is only an informal program development aid. The pseudocode statement, calculate and print the class average, can be refined as, if the counter is not equal to 0, set the average to the total divided by counter, print the average, else print no grades were entered. We're careful here to test the possibility of division by 0, a logic error that, if undetected, would cause the program to fail or produce an invalid output. Implementing sentinel-controlled iteration. Implementing sentinel-controlled iteration. In Figure 4.10, method main implements the pseudocode algorithms that we discussed earlier. Although each point is an integer, the averaging calculation is likely to produce a number with a decimal point, in other words, a real floating point number. The type int cannot represent such a number, so this class uses type tuple to do so. You'll see that the control statements may be stacked on top of one another in sequence. The while statement, lines 20 through 27, is followed in sequence by an if-else statement. Much of the code in this program is identical to that in Figure 4.8, so we concentrate on the new concepts. In Figure 4.10, you import java.utilscanner. That is what you typically do before you even put in the public class. itself initializes grade counter to 0 because no grades have been entered yet. Remember that the program uses sentinel-controlled iteration to input the grades. To keep an accurate record of the number of grades entered, the program increments grade counter only when the user enters a valid grade. Compare the logic for sentinel-controlled iteration used here for counter-controlled iteration in figure 4.8. In counter-controlled iteration, the while statement, lines 15 through 20 of figure 4.8, read a value from the user for a specific number of iterations. In sentinel-controlled iteration, the program reads the first value before reaching the while. The value determines whether the program's flow of control should enter the while body. If the condition is false, the user entered the sentinel value, so the while's body does not execute, i.e., no grades were entered. If, on the other hand, the condition is true, the body executes, and the loop adds the grade value to the total and increments the grade counter. Next, lines 25 through 26 in the loop body input another value from the user. Then, program control reaches the while's closing right brace. So execution continues by testing the while condition using the most recent grade to input by the user. The value of the grade was always input from the user immediately before the program tests the while condition, so the program can determine whether the value just input is the sentinel value before the value. If the sentinel input value, the loop terminates and the program does not add -1 to the total. For good programming practices in a sentinel control loop, prompts to remind the user of the sentinel. After the loop terminates, the if-else statement at lines 31 through 42 execute. The condition at line 31 determines whether any grades were input. If none were input, the else part of the if-else statement executes and displays the message, no grades were entered, and the program terminates. Braces in a while statement. Notice the while statement's block in figure 4.10. Without the braces, the loop will consider its body to be only the first statement, which adds the grade to the total. The last 3 statements in the block would fall inside the loop body, causing the computer to interpret the code incorrectly as follows. The preceding code would cause an infinite loop in the program if the user did not input the sentinel -1 at line 17. Common programming error. Omitting the braces that delimit a block can lead to logic errors such as infinite loops. To prevent this problem, some programs enclose the body of every control statement in braces, even if the body contains only a single statement. Explicitly and implicitly converting between primitive types. If at least 1 grade was entered, line 33 calculates the averages of the grades. Recall from the integer division yielding an integer result. Even though variable average is declared as a double, if we had written the averaging calculation as double average equals total divided by grade counter semicolon, it would lose the fractional part of the quotient before the result of the division is assigned to average. This occurs because the total and grade counter are both integers, and integer division yields an integer result. Most averages are not whole numbers, so we calculate the class average in this example as a floating point number. To perform the floating point calculations with integer values, we must temporarily treat these values as floating point numbers in the calculation. Java provides the unary cast operator to accomplish this task. Line 33 uses the double cast operator to create a temporary floating point in its operand total. Using a cast operator in this manner is called explicit conversion or typecasting. The value stored in total is still an integer. The calculation now consists of a floating point value divided by an integer grade counter. Java can evaluate only arithmetic expressions in which the operands types are identical. To ensure this, Java performs an operation called promotion or implicit conversion on selected operands. For example, in an example containing int and double values, the int value is promoted to double is a unary operator. It takes only one operand. Java also has a unary plus and minus operators, so you can write expressions like -7 or +5. Cast operations associate from right to left and have the same precedence as other unary operators. The precedence is one level higher than that of multiplicative operators. We indicate the cast operators with the notion type in our precedence charts to indicate that any type name can be used to form a cast operator. Line 30 of figure 4.10 displays the class average. In this example, we display the class average rounded to the nearest hundredth. The format specifier %.2f in printf's format control string indicates the variable's average value should be displayed with 2 digits of precision to the right of the decimal point, indicated by .2 in the format specifier. The 3 grades entered during the sample execution total 257, which yields the average 85.666. Method printf uses the precision in the format specifier to round the value to the specified number of digits. In this program, the average is rounded to the hundredth position and is displayed as 85.67. Floating point number precision. Floating point numbers are not always 100% precise, but they have numerous applications. For example, when we speak of a normal body temperature of 98.6, we do not need to be precise to a large number of digits. When we read the temperature on the thermometer as 98.6, it might actually be 98.5999, etc. Calling this number simply 98.6 is fine for most applications involving body temperatures. Floating point numbers often arise as a result of division, such as in this example's class average calculation. In conventional arithmetic, when we divide 10 by 3, the result is 3.333, with a sequence of 3's repeating infinitely. The computer allocates only a fixed number of space to hold such a value, so clearly the number in floating point value can only be an approximation. Owing to the imprecise nature of floating point numbers, type double is preferred over the type float because doubles variables can represent floating point numbers more accurately. In this reason, we primarily use the type double throughout this book. In some applications, the precision of float and double variables will be inadequate. For precise floating point numbers, such as those required by monetary calculations, Java provides class big decimal, which we'll discuss in Chapter 8. 4.11 Formulating Algorithms, Nested Control Statements. For the next example, we once again formulate an algorithm by using pseudocode and top-down stepwise refinement, and write a corresponding Java program. We've seen that control statements can be stacked on top of one another in sequence. In this case study, we examine the only other structured way control statements can be connected, namely by nesting one control statement within another. Consider the following problem statement. A college offers a course that prepares students for a state licensing exam for real estate brokers. Last year, 10 of the students who completed this course took the exam. The college wants to know how well its students did on the exam. You've been asked to write a program to summarize the results. You've been given a list of these 10 students. Next to each name is written a 1 if the student passed the exam or a 2 if the student failed. Your program should analyze the results of the exam as follows. 1. Input each test result. A 1 or a 2. Display the message enter result on the screen each time the programmer requests another test result. Count the number of test results of each type. Display a summary of the test results indicating the number of students who passed away and the number who failed. If more than 8 students passed the exam, print bonus student structure. After reading the problem statement carefully, we make the following observations. 1. The program must process test results for 10 students. A counter control loop can be used because the number of test results is known in advance. 2. Each test result has a numeric value, either a each time it reads a test result, the program must determine whether it's a 1 or a 2. We test for a 1 in our algorithm. If the number is not a 1, we assume that it's a 2. Two counters are used to keep track of the exam results. One to count the number of students who passed the exam, and one to count the number who failed. After the program has processed all results, it must decide whether more than 8 students passed the exam. Let's begin the top-down stepwise refinement with a representation of the top. Analyze exam results and decide whether a bonus should be paid. Once again, the top is a complete representation of the program, but several refinements are likely to be needed before the pseudocode can evolve naturally into a Java program. Our first refinement is initialize variables, input the 10 exam results, and count passes and failures. Print a summary of the exam results and decide whether a bonus should be paid. Here too, even when we have complete representation of the program, further refinement is necessary. We now commit to specific variables. Counters are needed to record the passes and failures. A counter will be used to control the looping process, and a variable is needed to store the user input. The variable that which the user input will be stored is not initialized at the start of the algorithm because the value is input during each iteration of the loop. The pseudocode statement, initialize variables, can be refined as follows. Initialize passes to 0, initialize failures to 0, initialize student counter to 1. Notice that only the counters are initialized at the start of the algorithm. The pseudocode statement, input the 10 exam results, and count passes and failures, requires a loop that successfully inputs the result of each exam. We know in advance that there are precisely 10 exam results, so counter control looping is appropriate. Inside the loop, i.e. nested within the loop, a double selection structure will determine whether each exam result is a pass or a failure and will increment the appropriate counter. The refinement of the preceding pseudocode statement is then, while student counter is less than or equal to 10, prompt the user to enter the next exam result. Input the next exam result. If the student passed, add 1 to passes. Else, add 1 to failures. Add 1 to student counter. We use blank lines to isolate the if-else control structure, which improves readability. The pseudocode statement, print a summary of the exam results and decide whether a bonus should be paid, can be refined as followed. Print the number of passes. Print the number of failures. If more than 8 students passed, print bonus to instructor. Complete second refinement of pseudocode and conversion to class analysis. The complete second refinement appears in figure 4.11. Blank lines are also used to set off the while structure for program readability. This pseudocode is now sufficiently refined for Java. Initialize passes to 0. 1. 2. Initialize failures to 0. 3. Initialize students counter to 1. 4. While student counter is less than or equal to 10. 5. Prompt the user to enter the next exam result. 6. Input the next exam result. 7. If the student passed. 8. Add 1 to passes. 9. Else. 10. Add 1 to failures. 11. Add 1 to student counter. 12. Print the number of passes. 13. Print the number of failures. 14. If more than 8 students passed. 15. Print bonus to instructor. The Java class implements the pseudocode algorithm on 2 sample executions, are shown in figure 4.12. Lines 11 through 13 and 19 of main declare the variable that are used to process the examination results. Error prevention tip. Initializing local variables when they're declared helps you avoid any compilation errors that might arise from attempts to use uninitialized variables. While Java does not require the local variable initialization be incorporated into declarations, it values are used in an expression. The while statement loops 10 times. During each iteration, the loop inputs and processes one exam result. Notice that the if-else statement for processing each result is nested in the while statement. If the result is 1, the if-else statement increments passes, otherwise it assumes the result is 2 and increments failures. Line 30 increments student counter before the loop condition is tested again at line 16. After 10 values have been input, the loop terminates and line 34 displays the number of passes and failures. The if statement at line 37 through 39 determines whether more than 8 students pass the exam, and if so, outputs the message bonus to instructor. Figure 4.12 shows the input and output of 2 sample executions of the program. During the first, the condition at line 37 of method main is true. More than 8 students pass the exam, so the program outputs a message to bonus the instructor. The code from pseudocode to this would be import java.utilscanner. Always before the public static void main, if you're going to be using numbers, you want to import the scanner. Scanner input equals new scanner, system.in, semicolons, system.in was in parentheses. And now we initialize the variables. In declaration, int passes equals 0, semicolon, int failures equals 0, semicolon, int student counter equals 1, semicolon. Now we process 10 students using counter control loop. While in parentheses, student counter is less than or equal to 10, squiggly brackets, system.out.print, parentheses, quotes, enter result, 1 is equal to pass, 2 is equal to fail, semicolon. Int result is equal to input.next int, parentheses, semicolon. The if-else is nested in the while statement. If result is equal to 1, squiggly brackets, passes is equal to passes plus 1, semicolon, close squiggly brackets, else, squiggly brackets, failures is equal to failures plus 1, semicolon, squiggly brackets. We increment student counter, so loop eventually terminates. Student counter is equal to student counter plus 1. All the if-else, system.out, print result, in result equals input, and student counter, and that's all within the very first while control loop. Now we terminate phase, prepare and display the results. System.out.printf, passed, %d%f, failed, %d%f, comma, passes, comma, failures, close parentheses, semicolon. And we determine whether more than 8 students passed if, parentheses, passes greater than 8, squiggly brackets, system.out.println, bonus to instructor, semicolon, close squiggly brackets, end. 4.12 Compound assignment operators. The compound assignment operators enable you to abbreviate assignment expressions. For example, you can abbreviate the statement C equals C plus 3, semicolon, with an additional compound operator, plus equals as C plus equals 3. C plus equals 3 is the same as C equals C plus 3. The plus equals operator adds the value of the expression on its right and the value of the variable on its left and stores results in the variable on the left. Thus, the assignment expression C plus equals 3 adds 3 to C. In general, statements like variable equals variable operator expression, semicolon, or operators one of the binary operators plus, minus, star, division, represent, or others we discuss later in the text, and the same variable name is used, can be written in the form variable operator equals expression. Figure 4.13 shows an arithmetic compound assignment operators sample expressions using the operators and explanations of what the operators do. Be sure to use self-review exercise to learn about the subtle feature of compound assignment operators. 4.13 Increment and decrement operators. Java provides two unary operators for adding one or subtracting one from the value of a numeric value. These are the unary increment operator plus plus and the unary decrement operator negative negative. A program can increment by 1 the value of the variable called c using the increment operator plus plus rather than the expression c equals c plus 1 or c plus equals 1. An increment or decrement operator that's prefixed to, placed before, a variable is referred to as a prefix increment or prefix decrement operator, respectively. An increment or decrement operator that's postfixed to, placed after a variable, is referred to as the postfix increment or postfix decrement operator, respectively. So, if the operator is a plus plus prefix increment, a sample expression would be plus plus a, increment a by 1, then use the new value of a in the expression in which it resides. Plus plus postfix increment would be a plus plus. Use the current value of a in an expression in which it resides and increment a by 1. Prefix decrement would be negative negative b. Decrement b by 1, then use the new value of b in the expression in which b resides. And postfix decrement b negative negative, use the current value of b in an expression in which b resides, then decrement b by 1. So it's good to know. For prefix increment, the a comes before the plus plus. If it's postfix increment, the a comes before the plus plus. If it's prefix decrement, the b becomes before or after the negative negative. And if it's postfix, it becomes before. Post is first, pre is last. Using the prefix increment or decrement operator to add 1 to or subtract 1 from the variable is known as pre-incrementing or pre-decrementing. This causes the variable to be decremented by 1. Then the new value of the variable is used in the expression in which it appears. Using a postfix increment or decrement operand to add 1 to or subtract 1 from a variable is known as post-incrementing or post-decrementing. This causes the current variable of the variable to be used in the expression in which it appears. Then the variable's value is decremented by 1. A good programming practices is unlike binary operators, the unary increment and decrement operators should be placed next to their operators with no intervening spaces. Here would be the difference between the prefix increment and the postfix increment operation, described in figure 4.15. Public class increment, squiggly brackets. Public static void main. Demonstrate postfix increment operators below. Int is equal to c. Int c is equal to 5, semicolon. System.out.printf. C before post increment. %d, comma, c, semicolon, prints 5. System.out.printf. Post incrementing c, %d, %n, c++. That prints 5 as well. System.out.printf. C after post increment. %d, %f, c. That now prints 6. This will demonstrate prefix increment operator. C is equal to 5 again. System.out.printf. C before pre-increment. %d, %10, comma, c. Close, semicolon. That prints 5. System.out.printf. Double quotes. Pre-incrementing c, %d, %n, comma, ++c. semicolon, print 6. Line 7 initializes the variable c to 5, and line 8 inputs c's initial variable. Line 9 outputs the value of an expression c++. This expression post increments the variable c, so c's original value 5 is output. Then c's value is incremented to 6. Thus, line 9's output c's initial value 5 again. Line 10 outputs c's new value 6 to prove that the variable's value was indeed incremental in line 9. Line 15 resets c's value to 5, and line 16 outputs c's value. Line 17 outputs the value of a new expression plus c. This expression pre-increments c, so the value is incremented, then the new value 6 is output. Line 18's outputs c's value again to show that the value c is still 6 after line 17 executes. Simplifying statements with arithmetic compound assignment, increment and decrement operators. The arithmetic compound assignment operators and the increment and decrement operators can be used to simplify program statements. For example, the three assignment statements in figure 4.12, lines 23, 26, and 30, passes equal passes plus 1, failures equal failure plus 1, student counter equals student counter plus 1, can be written more concisely with compound operators. Passes plus 1 plus equals 1, semicolon, failures plus equals 1, semicolon, student counter plus equals 1, with prefix increment operators as plus passes, semicolon, plus failures, semicolon, plus student counter, semicolon, or with postfix increment operators as passes plus failures plus student counter plus. When incrementing or decrementing a variable in a statement by itself, the prefix increment or postfix increment forms have the same effect, and the prefix decrement and postfix decrement forms have the same effect. It's only when the variable appears in the context of a larger expression that pre-incrementing and post-incrementing the variable have different effects. Attempting to use the increment or decrement operator on an expression other than one to which a value has been assigned is a syntax error. For example, writing plus parentheses x plus 1 is a syntax error because x plus 1 is not a variable. Figure operator precedence and associativity. Figure 4.16 shows the precedence and associativity of the operators we've introduced. They are shown from top to bottom in decreasing order of precedence. The second column describes the operator's associativity. The conditional operator plus colon. The unary operators increment plus, decrement negative, plus, and minus. The cast operators and the assignment operators equals, plus equals, minus equals, times equals, divided equals, and percent equals from right to left. The other operators as associate from left to right. The third column lists the type of each group of operators. 4.14 Primitive types. The table in Appendix D lists the 8 primitive types. In Java, like C and C++, Java requires all variables to have a type 2. In C and C++, programmers frequently have to write separate versions of programs to support different computer programs, because the primitive types are not guaranteed to be identical from computer to computer. For example, an int on one machine might be represented by 16 bytes of memory, on a second machine by 32 bits, and on another machine by 64 bits. In Java, int values are always 32 bits. A portability tip is the primitive types of Java are portable across all computer platforms that support Java. Each type in Appendix D is listed with its size in bits and its range of values. Because the designers of Java want to ensure portability, they use internationally recognized standards for character formats. An extra to this video, I wanted to add switch multiple selection statement. And I thought this would be a good bonus. Extra time to let you relax, extra time to allow your subconscious to learn. So without further ado, here is the next info. 5.6 Switch multiple selection statement. Chapter 4 discussed the if selection statement and the if else double selection statement. The switch multiple selection statement performs different actions based on the possible values of a constant integral expression of type byte, short, int, or char. The expression may also be string, which will be demonstrated in section 5.7. Using the switch statement to count A, B, C, D, and F grades. Figure 5.9 calculates the class average of a set of user-entered numeric grades. The program's switch statement determines whether each grade is the equivalent of an A, B, C, D, or F, and increments the appropriate grade counter. The program also displays a summary of the number of students who receive each grade. Like earlier versions of the class average problem, the main method of the class letter grades declares the local variables total and grade counter to keep track of the sum of the grades entered by the user and the number of grades entered. Respectively, lines 9 through 13 declare counter variables for each grade category. Note that the variables in lines 7 through 13 are explicitly initialized to 0. Method main has two key parts. Lines 24 through 48 read an arbitrary number of integer grades from the user using sentinel-controlled iteration. Update instance variables total and grade counter, and increment an appropriate letter grade counter for each grade entered. Lines 51 through 72 output a report containing the total of all grades entered, the average of the grades, and the number of students who received each letter grade. Let's examine these parts in detail. Lines 17 through 21 prompt the user to enter integer grades and to type the end-of-file indicator to terminate the input. The end-of-file indicator is a system-dependent keystroke combined which the user enters to indicate that there's no more data to input. In Chapter 15, Files, Input-Output Streams, NIO, and XML serialization, you'll see how the end-of-file indicator is used when a program reads its input from a file. On Unix, Linux, Mac OS systems, end-of-file is entered by typing the sequence Control-D on a line by itself. The notation seems to simultaneously press both the Control keys and the D key. On Windows systems, end-of-file can be entered by typing Control-C. The while statement, lines 24 to 48, obtain the user input. Conditions at line 24 called scanner method has next to determine whether there's more data to input. This method returns the Boolean value true if there's more data, otherwise it remains false. Then returned value is then used as the value of a condition in the while statement. Method has next returns false once the user types the end-of-file indicator. Line 25 inputs a grade value from the user. Line 26 adds grade to total. Line 27 increments grade counter. These variables are used to compute the average of the grades. Lines 30 through 47 use a switch statement to increment the appropriate letter grade counter based on the numeric grade entered. Processing the grade. The switch statement, lines 30 through 47, determines which counter to increment. We assume that the user enters a valid grade in the range 0 through 100. A grade in the range 90 through 100 represents A, 80 to 89 represents B, 70 to 79 represents C, 60 to 69 represents D, and 0 to 59 represents F. The switch statement consists of a block that contains a sequence of case labels and an optional default case. These are used in the example to determine which counter to increment based on the grade. When the flow of control reaches the switch, the program evaluates an expression in the parentheses, grade divided by 10, following keyword switch, and the switch's controlling expression. expression value, which must evaluate to an integral value of type char, be short or int, or to a string. With each case label, the controlling expression in line 30 performs integer division, which truncates the fractional part of the result. Thus, when we divide a value from 0 to 100 by 10, the result is always a value from 0 to 10. We use several of these values in our case labels. For example, if the user enters integer 85, the controlling expression evaluates to 8. The switch compares 8 with each case label. If a match occurs in case 8 at line 35, the program executes that case's statement. For the integer line 8, line 36 increments B count because the grade in the 80s is a B. The break statement, line 37, causes program control to proceed with the first statement at the switch. In this program, we reach the end of the while loop, so control statements to the control continuation condition in line 24 to determine whether the loop should continue executing. The cases explicitly test for the values 10, 9, 8, 7, and 6. Note that cases at line 31 through 32 that test for the values 9 and 10, both of which represent the grade A. Listing cases consecutively in this manner with no statements between them enables the cases to perform the same set of statements. When the controlling expression evaluates to 9 or 10, the statements in line 30 to 34 will execute. The switch statement does not provide a mechanism for testing ranges of values, so every value we need to test will be listed in a separate case. Each case can have multiple statements. The switch statement differs from other control statements so that it does not require braces and multiple statements in a case. Case without a break statement. Without break statements, each time a match occurs with the switch, the statements for that case and subsequent cases execute until a break statement or the end of the switch is encountered. This is often referred to as falling through to the statements in subsequent cases. A common programming error is forgetting a break statement when one is needed in a switch, and that results in a logic error. The default case. If no match occurs between the controlling expression and the case label, the default case executes. We use the default case in this example to process all controlling expression values that are less than 6, that is, all failing grades. If no match occurs and the switch does not contain a default case, program control simply continues with the first statement after the switch. Error prevention tip 5.9. In a switch statement, ensure that you test all possible values of the controlling expression. Displaying the grade report. Lines 51 through 72 output a report based on the grades entered. The line 54 determines whether the users entered at least one grade. This helps us to avoid dividing by 0. If so, line 56 calculates the averages of the grades. Line 59 through 68 then output the total of all the grades, class average, and the number of students who received each grade. If no grades were entered, line 71 outputs an appropriate message. The output of figure 5.9 shows a sample grade report on 10 grades. Switch statement UML activity diagram. Figure 5.10 shows the UML activity diagram for a general switch statement. Most switch statements use a break in each case determining the switch statement after processing the case. Figure 5.10 emphasizes this by including break statements in the activity diagram. The diagram makes it clear that the break statement in the end of the case causes control to exit the switch statement immediately. The break statement is not required for the switch's last case, or the optional default case which at last appears, because execution continues with the next statement after the switch. Displaying the grade report. Lines 51 through 72 output a report based on the grades entered as shown in the input-output windows. Line 54 determines whether the users entered at least one grade. This helps us avoid dividing by 0. If so, line 56 calculates the average of the grades. Line 59 through 68 then outputs the total of all the students who received each letter grade. If no grades were entered, line 71 outputs an appropriate message. The output in figure 5.9 shows a sample grade report based on 10 grades. Switch statement UML activity diagram. Figure 5.10 shows the UML activity diagram for a general switch statement. Most switch statements use a break in each case to terminate the switch statement after processing the case. Figure 5.10 emphasizes this by including break statements in the activity diagram. The diagram makes it clear that the break statement at the end of the case causes control to exit the switch statement immediately. The break statement is not required for the switch's last case or the optional default case when it appears, because execution continues with the next statement after the switch. Notes on the expression in each case of a switch. When using a switch, remember that each case must contain a string or a constant integral expression, that is, any combination of integer constants that evaluates to a constant integer value. An integer constant is simply an integer value. In addition, you can use character constants, specific characters in single quotes, such as a, 7, or $, which represent the integer values of characters. The expression in each case can also be a constant variable, a variable containing a value which does not change for the entire program. Such a variable is declared with the keyword final. Java has a feature called enum types, which we also present in Chapter 6. Enum type constants can be used in case labels. In Chapter 10, Object-Oriented Programming, Polymorphism, and Interfaces, we present a more elegant way to implement switch logic, which we use a technique called polymorphism to create programs that are often clearer, easier to maintain, and easier to extend than programs using switch logic. Well, thank you for listening to Programmer ASMR Chapter 4.